Applications with maxima and minima can be done depending on the generated function from the premise. This video talks about maximizing an entity but using derivatives of trigonometric functions. You are in differential calculus. The problem involves a trapezoidal gutter made from a 24 centimeter wide galvanized iron sheet. The base of the gutter is 16 cm, and we are to determine the top width if we maximize its capacity. Since there is no given length for the gutter, we are to work with the area of the trapezoid. The trapezoid has a base width of 16 cm, and having a GI sheet of 24 centimeters, this means that the sides of the gutter has lengths of 4 cm to come up with 24 centimeter perimeter. We are to identify the top width of the gutter to maximize its capacity. In order to solve for that, let's identify some dimensions. With no information about the height, let us tag this as h. If the bottom base is 16, the base width can be reflected to the top, where the excess are designated as x, making the top width as 16 plus twice of x. Take the area of a trapezoid. There are different options to do this. So let's start with the first, using the area of half of the height multiplied by the summation of the parallel bases b1 and b2. This function has four variables: the area, the height, base width, and the top width. We are to reduce this number to 2 before differentiating. Let us then introduce an angle to come up with trigonometric functions. Say we place theta on the bottom base triangle. Cosine of theta is then the adjacent side h over the hypotenuse of 4 cm. So h is cosine of theta times 4. Sine of theta is also taken as the opposite side x over the hypotenuse, making x of 4 sine of theta. Plug these two functions into the area of the trapezoid, making half of 4 cosine theta times the bottom base of 16 plus the top width of 16 plus 2x. Simplify the terms and have 2 cosine of theta times the binomial 32 plus 2x. Distribute 2 cosine theta and get 64 cosine theta plus 4x cosine of theta. This function has then three variables: the area A, the angle theta, and x. Transform x into theta and have A as equal to 64 cosine of theta plus 4 times 4 sine of theta times cosine of theta. Simplify this again and have A as 64 cosine of theta plus 16 sine of theta times cosine of theta. The function now have just two variables, A and theta, so we can then differentiate to maximize the area. The first term only has the derivative of cosine theta. The second term has two terms, being sine theta and cosine of theta, and this requires differentiation through power rule. dA over d theta is then 64 times the derivative of cosine, which is negative sine of theta, with d theta over d theta. The second term is differentiated as 16 with the first term sine theta times the derivative of cosine theta plus cosine of theta with the derivative of sine of theta. dA over d theta is maximized, making it 0. d theta over d theta on the first term is simplified as 1. The function is then 0 as equal to negative 64 sine theta plus 16 sine of theta times negative sine of theta with d theta over d theta plus 16 with cosine of theta times cosine theta with another d theta over d theta. The derivative of theta with respect to theta is cancelled out to 1. So the function then becomes 0 as equal to negative 64 sine of theta minus 16 sine squared of theta plus 16 times cosine squared of theta. Now the function is in terms of sines and cosines. And since there are more signs, we can transform the cosine to easily manipulate the function. To transform cosine into sine, use Pythagorean identity, which states cosine squared theta is equal to 1 less sine squared of theta. Plug this identity into the function and get 0 as equal to negative 64 sine theta minus 16 sine squared theta plus 16 times the identity 1 minus sine squared of theta. Next is to distribute 16 into the terms of the binomial, thus having 0 as equal to negative 64 sine theta minus 16 sine squared theta plus 16 minus 16 sine squared theta. Collect similar terms and get 32 sine squared theta plus 64 sine theta minus 16 as equal to 0. Reduce the coefficients and get 2 sine squared theta plus 4 sine of theta minus 1 as equal to 0. Although it has some trigonometric functions, this is a quadratic degree, so let's solve for sine theta using quadratic formula. To easily visualize it, we can let x equal to sine theta, making the function simpler as 2x squared plus 4x minus 1 as equal to 0. Plug the coefficients into the quadratic formula and have x1 as negative 2 plus the root of 6 over 2, which is 0.2247. The other x is negative 2 minus the root of 6 over 2, which is negative 2.2247. Since we are solving a dimension, the negative answer is not feasible, so we use x, which is sine theta, as 0.2247. From the derivation earlier, sine theta was x over 4, giving x as 0.8988. So we can then compute for the top width of the trapezoid, which was taken earlier as 16 times 2x, which is 0.8988. Thus giving 17.7976 centimeters. Going back to the start, another option is taking the area of the trapezoid as breaking it in a rectangle and two triangles, giving A as 16h plus twice of half of xh. The 2's cancel out, giving A as 16h plus xh. Since we haven't touched the location of theta, cosine theta is h over 4, which gives h as 4 cosine of theta. Sine theta is x over 4, where x is 4 sine of theta. A is then 16 times 4 cosine theta plus x of 4 sine theta times h of 4 cosine of theta. Simplify the terms and have A as 64 cosine theta plus 16 sine theta times cosine of theta. With A being in terms of thetas, we can then differentiate the function. Then again, the second term contains sine theta with cosine of theta, two terms requiring the differentiation through product rule. The differentiation then becomes dA over d theta as equated to 64 times negative sine of theta with d theta over d theta, plus 16 times sine of theta with the derivative of cosine theta plus cosine theta times the derivative of sine theta. The derivative of area is zeroed out. Then d theta over d theta is 1, giving 0 as equal to negative 64 sine theta plus 16 sine theta times negative sine of theta with d theta over d theta, plus 16 cosine theta times cosine theta with d theta over d theta. D theta over d theta is 1, making the function 0 as equal to 64 sine of theta minus 16 sine squared theta plus 16 cosine squared theta. With signs from the other terms, cosine should be transformed, and this is done by using identities. The Pythagorean identity states cosine squared theta is equal to 1 less sine squared of theta. The function then becomes 0 as equal to negative 64 sine of theta minus 16 sine squared theta plus 16 times 1 minus sine squared theta. Distribute 16 into the binomial terms, making 0 as equal to negative 64 sine theta minus 16 sine squared theta plus 16 minus 16 sine squared theta. Collect similar terms and get 32 sine squared theta plus 64 sine theta minus 16 as equal to 0. By reducing the coefficients, the function becomes 2 sine squared theta plus 4 sine of theta minus 1 as equal to 0. The function then can be simplified into 2x squared plus 4x minus 1 as equal to 0. Using the quadratic formula, simplifying sine theta as x is then 0.2247 and negative 2.2247, where the second x value is not feasible. Adopting x as 0.2247, its sign is x over 4, giving out x as 0.8984. This width of the triangles in the trapezoidal area. So the top width is solved as 16 plus twice of x, which then is 17.7976 centimeters. What if theta is taken elsewhere? Instead of locating theta inside the trapezoid, theta is placed right outside. Cosine theta is then x over 4, which makes x as 4 cosine of theta. Sine of theta is also h over 4, where h is 4 sine of theta. The function of area is then 16 times 4 sine theta plus 4 cosine theta times 4 sine of theta, which then is reduced as 64 sine theta plus 16 sine of theta with cosine of theta. With just a and theta left in the function, differentiate it, still having two terms in the second term, which means we will still use product rule. The function's differentiation then is dA over d theta as equal to 64 cosine theta times d theta over d theta plus 16 times sine theta with the derivative of cosine theta plus cosine of theta with the derivative of sine theta. The derivative of the area is zeroed out, and d theta over d theta is reduced to 1. The function then is 0 as equal to negative 64 cosine of theta minus 16 sine squared theta plus 16 cosine squared of theta. In this case, there are two cosine terms and a single sine term, which means we are to convert sine this time. Still using Pythagorean identity, sine squared of theta is equal to 1 less cosine squared of theta. Plug this into the function, then distribute 16 among the terms of the binomial to have 0 as equal to negative 64 cosine theta plus 16 minus 16 cosine squared of theta minus 16 cosine squared of theta. Collect similar terms and reduce the function into 32 cosine squared theta plus 64 cosine theta minus 16 as equal to 0. Reduce the coefficients to have 2 cosine squared theta plus 4 cosine theta minus 1 as equated to 0. The function's outcome is 2 cosine squared theta plus 4 cosine of theta minus 1 as equal to 0. The same function configuration that we can use quadratic formula, but x this time is cosine of theta. Still bringing the same function with x, which is still x of 0.2247 and negative 2.2247. The latter value is disregarded, then taking cosine theta as 0.2247, Cosine theta is also x over 4, where x is solved as 0.8988, which still provides the top width as 16 plus 2x, solved as 17.7976 centimeters. Theta can also be placed somewhere on the other vertex of the triangle, and by using the area of the trapezoid, correlate dimensions by taking cosine of theta, which is then the adjacent side x, over the hypotenuse of 4 cm. So x is 4 cosine of theta. The sine of theta is also the opposite side h over the hypotenuse of 4, giving h as 4 sine of theta. Plug these conversions into the area and come up with A as equal to 16 times 4 sine of theta plus 4 cosine theta with 4 sine of theta, which is simplified as 64 sine theta plus 16 sine theta times cosine of theta. This is the same function we came out in the previous cases.